Hi dear students, today we have a session on moments and moment generating function.
There are two types of moments we know, row moments and central moments. And by the definition of kth row moment about 0 for the random variable x is equal to expectation of x raised to k. And if x is discrete, the equation is summation over x raised to k, p of x, where p of x is the PMF of the random variable x. If x is continuous, it is equal to integral minus infinity to plus infinity x raised to k fx dx, where fx is the probability density function of the random variable x. And the kth central moment of the random variable x, that is mu k0, which is equal to expectation of x minus mu the whole raised to k. Here also there are two cases arise. If x is discrete, it is equal to summation over x minus mu the whole raised to k p of x, where p of x is the PMF of the discrete random variable x. And if it is continuous, integral minus infinity to plus infinity x minus mu the whole raised to k fx dx. And here we have a special case that is mu1, the expectation of x. We'll put k is equal to 1. It is the first moment of x. Then we can see that moment generating function. Moment generating function of a random variable x, mxt, the definition is expectation of e raised to tx. If x is discrete, it is equal to summation over x, e raised to tx, p of x. And if x is continuous, integral minus infinity to plus infinity e raised to tx, fx dx. You can see some examples for this moment generating function. Consider the first example, the binomial distribution. The parameters are n and p. mxt is equal to expectation of e raised to tx. It is equal to summation over x, e raised to tx, p of x. The binomial PDF is ncx p raised to x 1 minus p raised to n minus x. We'll substitute this PDF of that is p of x in this equation. We'll get summation over x is equal to 0 to n e raised to tx ncx p raised to x 1 minus p raised to n minus x. And this is equal to combining this p raised to x term and e raised to tx term. Then this is again equal to summation over x from 0 to n ncx e raised to t p the whole raised to x 1 minus p raised to n minus x. And this is equal to summation from x is equal to 0 to n ncx a raised to x b raised to n minus x, and this is the binomial expansion of a plus b the whole raised to n. Substitute for the value of a and b, will get e raised to tp plus 1 minus p the whole raised to n. The second example is Poisson distribution. The parameter is lambda. The Poisson PMF is p of x lambda raised to x e raised to minus lambda by x factorial. X is from 0 to infinity. The moment generating function of this Poisson distribution mxt, expectation of e raised to tx, is equal to summation over x e raised to tx p of x is equal to summation over x is from 0 to infinity e raised to tx lambda raised to x by x factorial e raised to minus lambda. Here we can take e raised to minus lambda outside the summation and combining this lambda term and e raised to t, and we'll get that it is equal to e raised to minus lambda summation from 0 to infinity lambda e raised to t the whole raised to x by x factorial. And this is equal to e raised to minus lambda e raised to lambda e raised to t, because e raised to u is equal to summation from x is equal to 0 to infinity u raised to x by x factorial. Just substitute the u value here, that is e raised to lambda e raised to t. Combining this e raised to minus lambda and e raised to lambda e raised to t will get e raised to lambda outside into e raised to t minus 1. The next is exponential distribution. This exponential distribution is continuous distribution. Here f of x is equal to lambda e raised to minus lambda x. X is greater than or equal to 0. The moment generated function, the same definition, mxt is equal to expectation e raised to tx. But we'll use integration instead of the summation because x is continuous, which is equal to integral minus infinity to plus infinity e raised to tx fx dx is equal to integral 0 to infinity because the variable ranges from 0 to infinity, hence we will use 0 to infinity e raised to tx lambda e raised to minus lambda x dx. Here also we'll combine e raised to tx and e raised to minus lambda x, then integral 0 to infinity lambda into e raised to t minus lambda x dx. Just simple in integration here we can use lambda e raised to t minus lambda x by t minus lambda within the range 0 to infinity. Apply the upper limit and the lower limit. The final answer is lambda by lambda minus t, where t less than lambda and which is undefined if t greater than or equal to lambda. Now we can see that some properties of moment generating function. Property number 1, mx0 is equal to 1, that is mxt. Here you put t is equal to 0. We can see that expectation e raised to 0 into x, that is expectation of 1, this expectation of a constant is equal to 1, that is a property of expectation. And this property satisfy the following distribution: binomial distribution, Poisson distribution, exponential, standard normal, and gamma distribution, etc. The second property is very important property. mxt is equal to 1 plus mu1t plus mu2 by 2 factorial t square plus mu3 by 3 factorial t cube plus etc. mu k by k factorial t raised to k plus etc. We use the expansion of the exponential function e raised to u is equal to 1 plus u square by 2 factorial plus u cube by 3 factorial plus etc. u raised to k by k factorial plus etc. We can see that mxt is equal to expectation of e raised to tx, that is expectation of expanding this e raised to tx. Using the above expansion, we'll get expectation of 1 plus, substitute u for tx, and 1 plus tx plus t square by 2 factorial x square plus t cube by 3 factorial x cube plus etc. t raised to k by k factorial x raised to k plus etc. Take the expectation inside the bracket. 1 plus expectation of 1 is 1 itself, that is 1 plus t into expectation of x plus t square by 2 factorial expectation of x square plus t cube by 3 factorial expectation of x cube plus etc. t raised to k by k factorial expectation of x raised to k plus etc. is equal to 1 plus t mu 1 plus t square by 2 factorial mu 2 plus t cube by 3 factorial mu 3 plus etc. t raised to k by k factorial plus etc. mu k plus etc. That means from this moment generating function we will get all the moments by comparing t raised to the coefficient of t raised to k by k factorial. The coefficient of t raised to k by k factorial is the rth moment. That is, this function generates all the moments, hence the name moment generating function. And we can simply generate this moment generating function, all the moments from this moment generating function using the next property also. The next property That is, differentiate this moment generating function k times and t is equal to 0. Then put t is equal to 0. We can see that the answer is mu k, the rth moment. Mxt is equal to 1 plus mu 1 t plus mu 2 by t 2 factorial t square plus mu 3 by 3 factorial t raised to 3 raised to x plus etc. mu k by k factorial t raised to k plus etc. The first derivative with respect to t and put t is equal to 0. We can say see that the first step and the second step you put t is equal to 0. The answer is mu 1. Again differentiate with respect to t, that is second derivative m2 dash t is equal to mu 2 when you put t is equal to 0. Continuing, we can find this kth derivative of this moment generative function and put t is equal to 0, will get the kth moment. That is, this moment generative function generates all the moments. And the third property is very useful in determining the moments of a random variable x. Some examples are, for binomial distribution, the moment generating function mxt is equal to e raised to t p plus 1 minus p the whole raised to n. We can easily differentiate with respect to t and put t is equal to 0. We'll get the first moment and second moment and the third moment and so on. The next example is for Poisson distribution. Here also find the derivatives of this e raised to lambda into e raised to t minus 1. The first derivative, find the first derivative and put t is equal to 0. We'll get the first moment, and find again the second derivative and put t is equal to 0. We'll get the second row moment. For the exponential distribution, we can apply the same thing, that is finding the derivatives, the first derivative, the second derivative and third derivative. We can easily find the corresponding moments. Also, we can apply this property number 2 in order to find out the moments from this exponential MGF. That is, you just expand this MGF and find the coefficient of t raised to k by k factorial, and which is the kth moment. That is, from this moment generating function, we'll get all the moments by applying either the property number 2 or property number 3.
Thank you.